Hi students, this video is going to give you a little introduction into solutions. So this is a classification of matter, and we started the school year in the fall by talking about the different types of matter. We talked about pure substances and impure substances and elements and compounds and mixtures and this and that. Well, we've already hit this side of the graphic organizer over here, the pure substances side. We've talked about elements like iron and silver and carbon. And we've talked about compounds such as iron 3 chloride or sodium oxide, ammonium nitrate, those kinds of things. What we're going to be doing in this unit is focusing on this corner over here, which are the homogeneous mixtures. So if you remember, we talked about homogeneous versus heterogeneous mixtures, and it was dependent on whether or not the mixture was uniform throughout. And when you look at a solution like Kool-Aid, like salt water, you can't see the different components of the mixtures and it looks very evenly distributed throughout. That's a homogeneous mixture. In other words, a solution. So when you're talking about mixtures and solutions, it has to contain at least 2 different substances. Okay, and those 2 different substances are not chemically combined. That's why they're not compounds. So when you look at this over here, this far left picture, you have 2 different compounds, these red and white ones here, versus the one with the red, white, and green here in the middle. It could contain a combination of elements and compounds, such as this picture here in the middle, where you have these black elements versus the blue and white compounds or molecules. And then over here on the right side, you have 2 different types of diatomics. In all of these pictures, though, the 2 different types of substances are not joined together. They are separate from each other. That's what makes them a mixture and not a compound themselves. Now, there's different parts of the solution. When we're talking about a solution, this is when we have a solute and a solvent combined. So a solute is the substance that gets dissolved. The solvent is the substance that does the dissolving. Now, the solute can be any state of matter. It could be a solid, a liquid, or a gas. Typically, we refer to them as solids because a lot of times in chemistry, that's what we're working with, a solid dissolved in water usually, but it doesn't have to be the case. The solvent here, again, usually a liquid, but doesn't have to be. Now, we have special terminology to use when we're referring to a liquid solute and a liquid solvent, and that is the terms miscible and immiscible. So here in these 2 pictures, you can see this, you cannot tell the 2 different layers. They're evenly blended, uniform throughout. On this side, though, you can see 2 different layers in the liquids. It's like oil and water. If you put oil in water, the oil is going to float on the top, and you can actually see the differentiation between the water layer versus the oil layer. So miscible means where those 2 liquids can mix, and immiscible is where the 2 liquids do not mix. So on this slide here, you see all of our vocabulary. So you want to make sure that you take a minute and jot all of these vocabulary terms down. This is what we were just talking about on the last slide with those pictures. As far as solubility goes, so we can talk about solubility in 2 different ways, solids versus gases. Solubility is just referring to the ability of a solute to dissolve in a solvent, okay? And sometimes, and you saw this during the like dissolves like lab that we did during IMFs, but sometimes something can dissolve in something, but it doesn't all the way dissolve. And that could be because you just have too much solute to dissolve in your given solvent. So solubility is the ability to dissolve. Can it dissolve? Does it fit that principle of like dissolves like? Now, what kinds of things can affect the solubility? We can get more solid solute to dissolve in our solvent by doing one of 3 things. We can stir. I do this all the time when I make my hot chocolate. I pour in my powder, add in my liquid, and I stir it up to make sure it dissolves all the way. When I make my little caffeinated drinks with my flavored water packet, I add it into my water. I use my straw to stir it up. to make sure that everything gets dissolved. I could also change the temperature. Most solid solutes can dissolve more at higher temperatures. So it's like when you're making your hot chocolate or your coffee. I'm not a coffee drinker, but if you make coffee, you are using hot water to make coffee. We're using hot water to make hot chocolate, and that's because it dissolves better at that higher temperature. And then we can also change the particle size. The particle size is going to change the surface area of the substance. Let me get my little annotate tool here because this one is a little bit tricky for students to understand. Let's say that we have a sugar cube. Okay, so this is like my 1 gram, excuse my drawing here. This is my 1 gram sugar cube. We can put that in our coffee and we can allow that to dissolve. It's going to take a little while, or I can break that up and I can add some granulated sugar. So now I've got smaller pieces of sugar. Let's say we have the same mass. This could be a 1 gram of granulated sugar as well, but this is going to dissolve much quicker and easier than the gram of sugar cube. This one has a lower surface area because only the outside of that cube is exposed to the solvent. So the solvent can only form attractive forces, intermolecular forces, with the sides of the sugar cube. That's why it takes so long for it to dissolve. This one over here, though, has a higher surface area because we have more sides of the sugar exposed to the solvent. So the solvent can form more interactions with the solid solute here and allow it to dissolve better. Okay, so that's what we're talking about. A smaller particle size, smaller size means that we have a greater surface area, which means that we have greater solubility. Okay. All right, let's look at what we got next here. Now, when we're talking about solids, solids are usually more soluble at higher temperatures like we were just discussing. It's not the same for gases. Gases are going to be more soluble at lower temperatures and high pressures. So when you think about soda, if you drink Cokes or anything like that, typically the Cokes are kept in a refrigerator. If you get them out of the fountain, drinks at, a restaurant or something, they come out cold. And that's because at that lower temperature, the gases can stay dissolved in the solution better. The attractive forces can be stronger because those gas particles aren't moving as quickly. If we start to increase that temperature, those gas particles start to move around really quickly and they can't form attractive intermolecular forces with the solvent as easily. The other way that we can keep gases more soluble is at higher pressures. So if you think about, again, your sodas, once you pop the tab on a can, twist the top on a bottle, you can hear that fizz as soon as you break the seal of the container. And that's because the pressure is starting to be released. As soon as the pressure starts to release, that gas starts to bubble up out of the soda, and the gas cannot stay in the solution as easily. It's not as soluble because it's at a lower pressure once you've opened the container. Okay, so that's your little introduction into solutions. If you have any questions about this material, be sure to let me know. Okay, thanks.